Hello and welcome to XC Psychology. Today we're going to try to answer the question, do molecules move without being pushed? Well, if we look at our everyday object, say a soccer ball here, usually it stays very still when no one is kicking or throwing or pushing it. We rarely see something like this, where the soccer ball is bouncing by itself. Unless we give the ball to Messi, and Messi will do some wonderful dribble with the ball. However, molecules work a bit differently. So even though we cannot see them, they kind of just always move constantly. So if we see this food dye being made into water, it kind of just dissolves. We're not mixing it, we're not shaking it. It kind of just dissolved in water by itself. So were they being pushed or were they not? Let's have a look. So here we have a still glass of water, not sparkling water, just a still glass of water. And with our eyeball, we can see that the water is very still. However, if we put the water into under a microscope, we will see that water molecules are constantly moving to different directions, and the directions seems to be very random. So at a macroscopic level, the water molecules are always moving. They're constantly moving, and they're constantly moving randomly. Because we have something, actually they have something called kinetic energy. And basically, we can understand that as an energy of motion, which is constantly moving. And here is a nice image of when a water molecule is moving inside the water. I think it's pretty cute. It's kind of like a little planet in our universe. So with the kinetic energy, one thing to note is that when the temperature is high, the molecule seems to move faster, and when the temperature is low, they seem to move a bit slower. And it's kind of like us. When it's summer or it's sunny outside, we tend to want to go out a bit more and do more activities. And when it is cold in winter, we kind of prefer to stay indoors and have a hot chocolate. And so if we look at this boiled water here, and we'll notice we have some bubbles and maybe some vapors on the top. If you can see in here, some little bit like steam or gas, or we call it vapor here, and the bubbles are bursting. So why does that happen? It is because when the water is still and is in, lower temperature, room temperature, let's say, and the water molecules kind of like just holding hands. They're very closely connected together, right? And when the temperature is high, they are moving around a lot more. And so with this, burst of energy, some of the water molecules will be physically break away or break free from their hand-holding friends, and hence create this water vapor. And you can say that those water molecules break free like Ariana Grande and let it go like Elsa, right? And so another thing to cause the water to break away or to cause the bubbling motion is the convection currents. The convection currents is basically, we have hot water constantly move up and the cold water constantly move down. That causes a little bit of a bubbling motion that we see in the boiling water. Now, we have a concept called Brownian motion. Don't worry about it for now. We'll dive into the details in next section. But what happens is when we have boiling water and the water vaporizes, right? The water breaks away from their hand-holding friends. They kind of just, entered into our room. And what will happen is these molecules will be attracted or move from a high concentration to low concentration. So it will spread across our room. So sometimes when we're making soup or we're boiling water for a cup of tea, we'll notice that maybe the humidity in our room has increased. This is because of the diffusion process. The water molecules that break away, they move from the high concentration to low concentration. So now we have a conceptual understanding of diffusion. Let's have a look at the person who discovered it. So Robert Brown, this gentleman with a very nice hairstyle here, is a Scottish botanist. He discovered what is now known as the Brownian motion in 1827. And what happened was he was studying a flower or a plant called Chloride ponchella. I hope I pronounce it right. And it's sometimes also known as the pink fairies, ragged robin, and deerhorn cloacia. And he was observing a grain of pollen. So here we have the pollen in the water, suspended in the water. And he noticed that the pollen is constantly randomly moving or darting or jiggling. And that's when he first discovered the phenomenon, but he couldn't explain it or he couldn't prove it until almost 80 years later, when Albert Einstein published his paper. I count the German, so in translation, it is on the motion of small particles suspended in a stationary liquid as required by the molecular kinetic energy of heat in 1905. So in 1905, Einstein was able to prove and explain that actually the pollen itself was not moving. It was the water molecule that's constantly pushing and combating the pollen to move. So now we have the conceptual and historical understanding of diffusion. Let's have a look at a practical example of diffusion in the human body. If you remember this lady from our last episode, she's very brave. She had a spoonful of table salt. And let's follow the journey of salt. So we have phase 1, which is passive ion diffusion. We have a high concentration of salt in our intestine or in our gut, and which means we have a higher difference or a steep concentration gradient between our gut and our bloodstream. Don't be intimidated by this word, steep concentration gradient. It just means the salt concentration is higher in the gut than in the blood. So remember, diffusion is the net movement from high concentration to low concentration, right? So now the ions would be traveling through their ion channels into our bloodstream, right? There's no ATP required at this stage, and we're just moving into the blood. And phase 2 is kind of interesting. Take it as a teaser for the future episode, is that we have something called co-transport, or the hitchhikers, which means that these doors will not open until 2 conditions are met. 1, we have a sodium ions binding or docking into the door. And 2, we have a glucose or amino acids also docking into the door. And then the door would open, and both the sodium ion and the glucose would travel into our bloodstream. So salt is actually very important for us because it helps us to absorb nutrients like glucose and amino acids. Next, we have our second diffusion because we have a high concentration of salt in our bloodstream, right? And we have very little water in here. You don't see many water molecules in here. And in our gut, we have a lot more water, right? And what will happen? We diffuse again. Remember diffusion, the net movement from high concentration to low concentration. Basically, the water follows the salt. And we have a situation called osmosis. And salt is an interesting thing because we can't have too much, because we'll have much, much more water following and our blood pressure will be skyrocketing, but we can't have too little because then we don't have enough water, we'll be, dehydrated. And that's it. That's the journey of salt. It involves two diffusions. So key takeaways for today, numero uno. Molecules are always moving, and because they have kinetic energy. And their movement is random and does not require an outside push. Number 3, higher temperature usually makes particles move faster. 4, when particles are crowded in one area, they spread towards areas of low concentration. 5, this net movement from high concentration to low concentration is diffusion. And in the body, diffusion is influenced by water, cell membranes, electrical forces, protein channels, and cellular energy. Question: if molecules are always moving and spreading out, why doesn't everything in the body eventually just mix together? Coming up next, why doesn't everything just mix together?